Started.
Yeah, thanks.
Good morning, everyone. Thank you for joining us today for Indian webinar series, Introduction to Computational Drug Design, co-organized by Schrodinger and PCI. I would like to take a moment to thank our collaborators for supporting us with this event. Also, the panelists from JSS and Manipal and the IT team from JSS for hosting these sessions. Today we have another demo session. Um, so today's demo session is about the binding site identification using our tool sitemap by Dr. Prajwal. So during the course of this presentation, if you have any questions, feel free to drop your queries in the chat section of the YouTube link, and we will take the questions in the Q&A session at the end of the session. Um, so without further ado, I would like to pass on the control to Dr. Prajwal.
Thank you very much, Shalviya. So, is it a time to start?
Yes, we can
Okay,
start.
great. So, let me just share my screen. So, could you please confirm whether everything is fine?
Yes, I see your screen. I can hear you.
Okay. So, I hope those control panel, you cannot see that one now.
No.
Okay, great. So, good morning, all of you, and thanks again for joining the presentation. So today we are going to see the binding site prediction and its analysis using the tool named called sitemap. So that sitemap tool is included in the Schrodinger suite. So you will have access for that sitemap tool, and I would say it is very critical tool when you don't have information about the bound ligand in the protein structure. Not only that, but even if you have information about bound ligand which is present in the protein structure, let's say from crystallography or from molecular docking, then also this tool is very useful to understand the binding site properties, and which you can use it for the heat optimization. So that's the reason why I'm saying this is very critical and important tool. So to my knowledge, like you will not get such tool in any other software with this vast understanding. So let's try to explore the tool and its usage. So before starting the presentation, I would like to remind you, so we had a webinar presentation which was streamed on 24th of September 2020. So it is on the YouTube. So you can always go to YouTube to know more about more basics about the sitemap analysis and the binding prediction tool. So that lecture you can view it on the channel of JSS Academy of Higher Education and Research. So you can just go to the channel, YouTube channel, and look for this particular presentation which was streamed on 24th of September. So I request you, if you haven't seen that basics presentation, you can always visit there and see it, and then you will understand what is basics and principles of it. So that's what is the thing, but still we don't need to worry about it at this point, because anyway I will try to brush up that knowledge whatever we discussed before starting the actual sitemap tool. So we discussed initially about the binding site, binding site and the protein receptor, which mostly resembles to the lock of your lock and key model, and substrate or inhibitor resembles to the key, and the whole idea is to find out the key. So but to find out the key, one must understand what is the internal structure of lock, like how it looks. So whenever we talk about lock, so that can have various levers. So similarly, whenever we talk about the protein structure or the receptor, it can have various properties. So those properties are like hydrogen bond acceptor property, hydrogen bond donor property, hydrophobic group, hydrophilic group, and this way there are many such properties. And the whole idea is you need to know that internal structure of protein or receptor. So to know more about that internal structure, we have a powerful tool called sitemap to do that analysis. And in our previous presentation we have also seen like protein is not at all static, but you can see the lock is static, but protein is not at all static. It always have dynamism whenever it is present in the body or whenever it is alive. So we also need to consider those factors, or you can analyze it using this sitemap tool. So how dynamism of protein changes, and accordingly how the binding site is being changed. So one more critical thing which we explored or which we discussed that day is the ligand molecule or inhibitor or substrate never ever binds to any other place in the protein structure. Though your protein structure is not even, it is always uneven surface, but there are many pockets or sub pockets, or there are many keys you can observe in the protein surface, but still there is very definite binding pocket for the inhibitor or the substrate or any ligand. So whole idea is to identify that specific pocket, which we call it as a binding pocket for a inhibitor. So because it's a definite, so it must follow a lot of different things, and our whole idea is to identify that pocket. So this is what the whole idea is, and we have seen like how one can use this particular information whatever is present in the binding pocket of the protein. So you can see there are various characteristics, for example hydrogen bond acceptor, hydrogen bond donor region, which is mentioned here in blue color. Hydrogen bond acceptor region of the ligand is shown in red patch, and yellow patch is for hydrophobic region. So these are the few characteristics which are present in the binding site that makes it definite binding pockets. So other way we have seen that if you look your protein structure or protein ligand complex in cartoons view, you might miss that pocket information. But at same point, if you look your protein into surface view, then you will able to see what are the various pockets or sub pockets present in the protein structure. And as I said, ligand always bind to the definite sub pocket. So here you can see how ligand is fitted inside the specific sub pocket, and this pocket is called as a binding pocket out of all those protein surface. So one can analyze it manually also by visual inspection, but through visual inspection you would miss many important aspects of the binding pockets, because those are not possible to view visually. So you can see like how the ligand is fitted inside the pocket, how it is exploring various sub pockets which are present in big binding pocket. And other than that, you can also see how the pocket gets extended to the extended region, and you can also use this information for your further heat optimization. And so we have seen here like how your pocket lies inside the binding pocket, which is shown in this blue color. And as you see your ligand, which is shown in this van der Waals view. So this ligand is occupying a small region of big binding pocket, and you can use this again, that empty pocket which is not yet explored by any of the ligand. We can modify your ligand in such a way that it occupies that extra space also to get the better binding. So this is the opportunity which you will get. So you can see that extended binding pocket might have different properties like hydrogen bond acceptor property, hydrogen bond donor property, or hydrophobic properties. So we can accordingly we can use this information to design our new ligand to get a better fitting. Not only that, we have also seen in our previous discussion like a same protein can have different crystal structures with the different ligand molecules present in it. And not only different ligand molecules, but you can have different biological activity for those ligand molecules. So based on that ligand molecule, your binding pocket, which is very dynamic in nature, occupies the different shape as a bioactive conformation. So one need to consider all those shapes. One need to study those all those shapes, like which type of ligand acquires which type of shape in which crystal structure. Though these all protein structures belong to the same protein called human aldose reductase, but still they can acquire different shape of binding pocket. So these are the things one need to consider in the drug designing project, and one should not ignore those things. So we need to always come up with the consensus and some reasonability about your project. So these are the things which you can get it from the sitemap analysis. Other aspect of binding pocket is a single protein structure can have multiple binding pockets. So for example, this is the example of human serum albumin which we have seen, and you can see this single protein structure has multiple binding pocket where diverse type of ligands, let's say from small size to bigger size ligand, can bind to this particular protein because this human serum albumin has a role in drug transportation or drug binding. So that's why this protein has a necessity to have multiple binding pockets where the ligand can fit, even diverse type of ligand can fit. So this is also one of the aspect which one need to see while designing your project. Other thing which we have seen is some protein can have a deep binding pocket where ligand can go inside it just like a key, and it can fit inside the protein binding pocket. Not only that, but protein can also have shallow binding pockets. So those shallow binding pockets are responsible for some binding of some other protein partner or allosteric it might act as an allosteric binding pocket which can have effect on orthosteric pocket. So these aspects also you can study using sitemap analysis, so one should not ignore. So whenever you are dealing with protein-protein interaction type of studies, you need to look for shallow binding pocket, and whenever you are looking for protein ligand studies, you can go for deep binding pocket. So these things can be explored through sitemap tool. And here you can see there is another partner protein which is shown in green color and bind to the same region where the shallow binding pocket is being predicted. So that's the experimental crystal structure of cytochrome BM3 and FMN domain. So you can visit this structure and see how actually it looks. So in detail, if you want to see this binding site analysis using sitemap, you will find different type of patches which represent different properties. For example, wherever you find the blue color patch is responsible for hydrogen bond donor region in the ligand molecule. So for example, in this particular ligand molecule, which is shown in ball and stick, you can see there is a nitrogen attached with hydrogen. So this group is act as a hydrogen bond donor from the ligand, and it is shown in the blue color patch. And the same way you will have red color patch which is responsible for hydrogen bond acceptor group in the ligand, and you can see this hydrogen bond acceptor, which is a carbonyl group, is able to accept the hydrogen bond from the amino acid residue. Not only that, in yellow color patch, you will it will show you the hydrophobic region which is present in the ligand molecule, and hydrophobic region is very critical, for successfully placing the ligand in hydrophobic binding pocket. So these are the properties which you will get it from the sitemap analysis, and we will see it in a detail. So how to see, how to look into sitemap result. So before that, we need to find the option where it is. So I expect so far you are very much familiar with the Maestro interface, and you know how to browse through the Maestro interface and how to see other options. So whenever you want to do this sitemap analysis, you will have option which is present in task, browse, and there is a application option called other applications, and in other application you will find the option called sitemap. The same thing, you can access it by simply typing sitemap in the search bar, and it will show you the option of sitemap. So please remember the name sitemap, which is of your interest. So once you will have this sitemap panel, you just need to load your protein structure and open the sitemap panel and click on run. It is pretty straightforward panel which has all default options which are working, which are definitely working with it. So with this sitemap option, you can not only predict the various binding pockets in the protein structure in case if you don't know about any binding pocket, or if in case if you don't have information about any binding pocket residue. So you can identify top rank potential receptor binding sites with this option, or in case if you have co-crystallized ligand pose or protein ligand complex with you, you can evaluate specifically that single binding site region if you use this second option. So what does it mean? It means like you have all type of options present with you. It's up to you which option you need to analyze. So if you have protein ligand complex, you in such case, instead of predicting lot of different binding pockets, you can simply analyze the single binding pocket region. If you have a opposed structure of protein and you don't know where ligand gets bind, so you can predict top rank potential receptor binding pockets. So these are the things which you have. Along with that, you also have an option to detect shallow binding pocket. In case, as I said, if you are working on protein-protein interaction studies or allosteric binding studies, in that case, you can use this option, detect shallow binding pocket, and it will predict such a binding pocket with a big in size. So that's it. I mean, most of the things with this sitemap panel is by default on, but if you want to customize it, then that's perfectly fine. You can customize it, just load your protein structure and run. So whenever I say protein structure, as I mentioned even before, like whenever we say protein structure, that protein structure must be prepared through protein preparation wizard. So whenever you have any protein structure, you must ask yourself a question whether I prepared this protein structure through protein preparation wizard or not. So if your answer is no, then definitely you need to open the protein preparation wizard panel, which option you will get here. And you need to prepare that three-step protein preparation wizard. And once you get your prepared protein out of it, then only it makes sense to run this sitemap panel. So again, I request you never ever go with such type of sitemap predictions with the crude protein structure. Always you need to do it with prepared protein structure. That's the must do thing. So this is the option, and in brief we have also discussed about what is the algorithm it follows, and in general it follows the this site point search. Means you can see there are various points which these are probe points which software puts in wherever it finds the pocket, and then the software tries to join all those points. If it gets joined, and if there is sufficient number of points which are present in the single pocket, it is predicted as the binding pocket. So software computes volume based on it. Software identifies various properties of binding pocket based on these probe points. So this is the overall algorithm which software follows. And this is the way the sitemap result looks like. It not only shows you the patches which are responsible for various properties, but it also shows you those points, probe points, which are shown here in the white color dots. So those are the same probe points which are there for the binding site identification. So other quantitative aspect of analyzing binding pocket is the various scores. So out of these various scores, you have very precise scores like D score. D score stands for druggability score. And whenever you have this druggability score more than one, like 1 point something, it is always considered as a very druggable site. So one need to consider this specific site as a druggable site. But if its value is less than 1, for example, zero point 0.9 or zero point 0.8, so you can also consider such sites as a probable binding site, but if its value is less than zero point 0.7 or zero point 0.6, then you can ignore those points, because according to druggability scores, so such binding pockets which has less or low druggability score is having no such druggability characteristics like hydrogen bond acceptor or donor type of features. So in that case, you can ignore such sites which are having less D score value. So always remember, if it is more than 1 point something, then you must consider this as a binding pocket. If it is zero point 0.8 or zero point 0.9, then you can consider it as a binding pocket. But if it is less than that, less than zero point 0.7 or zero point 0.6, then you can straight away ignore those sites. So same thing is also applicable for the site score and other parameters, like you have size or volume of the binding pocket. Based on that, you can see how much is the binding pocket volume. So this is the formula which is included for calculation of druggability score and site score, so that we have seen. And binding site volume, somebody may ask what is the unit of binding site volume. So it is always mentioned in angstrom cube. So let's see like how to specify this binding pocket for grid generation. So whenever you have co-crystallized ligand present in it, so it's pretty straightforward, as we have seen in previous tutorials. To perform grid generation, if binding site is definite and you know where the co-crystallized ligand is bound, so you can simply pick that for any atom of the ligand in the grid generation panel, and it will automatically identify it as a binding pocket, and software will generate a grid out of it. But there can be a case when there is no co-crystallized ligand present in it. So in such case, you will have sitemap results with you to help you out. So you will have these site points which are mentioned here in the white color. So you can use this site point information to generate a grid using grid generation panel. So you just need to change this particular option from molecule to entry, and then that's it. You just need to click on any of the point which is mentioned here in white color, any of the site point. Just click on it and it will automatically identify it as a binding pocket. So that is also pretty straightforward, and we will see actually how it looks in the Maestro. So now let's go to the Maestro and see. So this is what was the brief brush up of our previous knowledge, which we have already discussed on 24th of September webinar session. So let's see how it looks in the Maestro. So as you know, always like whenever you have Maestro icon which is present on your desktop, in case of Windows, you can always double click on this Maestro icon and it will start the Maestro. If you are using Linux, then the command is Maestro, Maestro. That's the command, and it will start the Maestro. In case of it, if it is MacBook, then you need to go to applications and you will find the option called Maestro. So you can start it from there. So once you start it, so you can see here I have already created a project for this particular exercise, which is for the sitemap analysis. And you can see here, whenever I say protein structure, I have always, whenever I load this protein structure, it is always in the prepared format. So you can see this entry, I am working with the PDB ID called 2p33. And whenever I have loaded this 2p33, I need to first prepare this protein structure through protein preparation wizard panel. So you can find this option here, and you need to go through these 3 clicks process for the protein preparation wizard. Like first is pre-process, then review, modify, refine, in which you need to optimize first, as explained by Dr. Kaushik yesterday, and you need to perform energy minimization on it. So once you prepared this protein structure, you will get the final prepared protein structure as output, and you can use this information for the prediction of binding site. This is what the protein is. So just as a test case, what I did, I have taken the protein structure of this protein called 2p33, which is prepared, and currently this protein structure doesn't have any ligand in it, as I have removed this ligand from the protein structure because I wanted to check whether sitemap is able to predict the exact binding pocket for the ligand molecule wherever the ligand molecule is present. Like for example, you can see as such ligand molecule is present somewhere here in the protein structure, and I have removed that particular ligand molecule from the place so that it makes the complete pocket empty. And in this way, I have made this protein structure in the form of APO. So right now, this protein structure has no ligand, but as I said, the protein structure surface is always uneven in nature. So you can see there are a lot of keys or a lot of subpockets are present around the protein structure, and you can, as usual, you can visually inspect which can be the various binding pockets. So by just visually inspecting the protein surface, I could not see where the exactly ligand can bind because there are many such sub pockets where ligand can fit. But by using sitemap tool, which I have mentioned, so let's go to the task, browse, and as I said, there is an option called other applications. In other applications, you will find the option called sitemap. So this is the sitemap tool. If you simply click on it, it will open the panel. So as such, all those default option works very fine. You don't need to worry about it. You just need to hit the run button. So here is the sitemap panel, and I'm just clicking on the run button. Once you click on the run button, it will run the job in background, and then it will give you the output results in the format of this sitemap. So you can see the sitemap results are loaded now for this particular protein structure. It's all automatic in the Maestro software. As I said before, Maestro is very user friendly. Whenever job get finished, it automatically loads the result in the Maestro table. So you don't need to look for the result somewhere else in the directory. It is automatically being loaded. So you can see there are various binding pockets which are predicted for this particular protein structure. And if I go through one by one, you can see there are 5 different binding pockets which are predicted through sitemap. So, and these are ranked according to the site score. So there is site 1, 3, 2, 5, 4. So means there are 5 different pockets, and last entry is for the protein. So you can see now we will try to explore how this particular protein looks like in the surface view, and we will see where are the various binding pockets which are being predicted. So we will proceed one by one. So let's see the site 1 where it is basically predicted. So you can see in this particular protein structure. So site 1 is predicted somewhere in the middle of this particular protein structure. So it is tentatively the same place where ligand was bound. So we will see it afterwards, but let's see now. This is looking like a biggest binding pocket which is predicted through sitemap. So which is at the middle of protein. Then just to get confirmation, so we will see the next binding site and see where it is basically present. So I'll just try to load the next binding pocket, and you can see this second binding pocket is predicted somewhere here, which is from the first binding pocket, but it also acquires some of the place here in the side of protein. So you can see that the second binding pocket, then we will look into third binding pocket where it is being predicted, and you can see it is predicted somewhere here, which is again small in size, but somewhere in the bottom of this particular protein. Then let's look into fourth binding site and see where it is being predicted. And if you rotate the protein, you will find it at exactly bottom. It found a small binding region where it is it says the binding pocket is being predicted. So, and if you see the the last binding pocket, you can see somewhere here it is being predicted. So in this way, there are various binding pockets which are being predicted for this particular protein structure. And if you see all those binding pockets in just one go, so I just load all pockets in the visualizer, and you can see the first binding pocket, which is almost present at the middle of this particular protein. Then there is a side binding pocket, then there is below there is another pocket, and then there is another pocket which is present somewhere here at the bottom. So in this way, the five top binding pockets are predicted so by the software, and our aim is to find out which is the exact binding pocket. So what we will do after analyzing all those things, we will try to see the quantitative way of analyzing this binding pocket by looking the scores in project table. So you can see project table button here on the top right. If you simply click on it, it will open the project table and you can see all those results from which you get it from the finding which you get it from the site map. So the same thing you can also observe through the property tree where all of the options are present. For example, in by default you will have number of rows and number of columns which are present in the project table, and you need to little bit scroll using this scroll button. It is same as that of Excel sheet, and you need to find where your exact results are. So this is the way one can analyze this result. But as I said, like there are many such columns present, so you need to browse through all those columns and see which are the columns of your interest. But the easiest way is the simply this property tree gives you the easiest way of viewing this result. So there are all properties which are mentioned here, so you just need to hide all properties using this tick button. Once everything gets hidden, you need to look for the particular section where the sitemap results are mentioned. So you can see the sitemap results are mentioned here. So there is a expansion button, so I just expand these results, look into primary properties, what are those, or there are also secondary properties, you can check it. But initially I'm interested only in primary properties, so I'll just click on the primary properties so that it shows me only primary properties. So this is the way you can specifically see your results instead of looking into the complete table or complete all columns in the table. So this is the way. Now only 4 columns are being shown, and out of 4 the column of my interest are site score and D score. So you can see the first site which is mentioned here has a D score of 1.044. So as I said, whenever you have site score value of more than 1 point, then definitely you need to consider it as a binding pocket. But if it is less than 7 or 6, less than zero point 0.7 or zero point 0.6, then you can ignore such pocket. So here, by looking at this result quantitatively, these scores, I can definitely see this binding site score and D score of the first site, which is predicted from the sitemap, is having score more than 1 point. So it means it is definitely a binding pocket. So let's try to see whether is it a really a binding site for inhibitor ligand or not. And rest of the site you can ignore because its value is like 0.7 or zero point 0.6, zero point 0.5 and zero point 0.4. So you can straight away ignore those as those pockets because those are not much druggable pockets. So the only pocket which is of my interest is the first site. And as a control, I'll try to see how this first site looks. So basically, as I said, this first pocket is predicted at the middle of this protein, and when because initially we have removed the ligand from this binding pocket just to make a control on the software. So we can simply load the same ligand which we have extracted from the binding pocket, and we can see it whether it is present at the same site or it is present at some other site. So you can see now your ligand, which we have mentioned, is also present at the same place where first binding pocket was predicted. So you can see the ligand is occupying the same site which is predicted by the software. But point to mention here is ligand is acquiring only small space of binding predicted binding pocket, but there are many other sub pockets also which are extended and which are connected to the main binding pocket. So you can design your ligand in such a way that it acquires all that extra positions. And again, while designing the ligand, you need to consider these properties like hydrogen bond acceptor property, hydrogen bond donor property, which are in red color, in blue color. So you can consider those property while making substitution in your existing ligand. So this is the way we can use this information for heat optimization. And this is also one of the way to make the control calculation and to get the reliability about software, that yes, software is predicting the exact same binding pocket which was already reported by the crystallographer. So in this way, it makes your software reliable, and this is the way you validate your sitemap results. So this is one of the way to see your results first of all. So other than that, we have also seen the example of human serum albumin protein. So for that, it has a PDB ID of 1A06. So that is the PDB ID of human serum albumin protein structure. So it's like a big protein structure you will have. So as I always said, whenever you have protein structure with you from the protein data bank, you must need to go through the protein preparation wizard, that three-step process. You need to pre-process it, you need to optimize hydrogen bonding network, you need to perform energy minimization on it. So once you go through this protein preparation wizard, then only you will have the protein structure in proper format. Then only the protein structure you call it as a protein structure. Otherwise, that whatever you get from protein data bank is the very crude structure, and one should not proceed with such structure. So you always remember, need to prepare your protein structure through protein preparation wizard. So this is one of the example of human serum albumin protein in apoform, means there is no ligand present in this protein structure. So in such protein structure, I run sitemap results on it. So let's try to see how it looks like. So I have again loaded the protein structure on the Maestro. Just go to sitemap and look, see what are the options present in it. So again, the same thing, just open sitemap and hit on run. It will show you all the binding pockets which are present in the protein structure. So we will try to see how it looks like one by one, and how many binding pockets software predict. So this is the surface view of protein, and then we will try to see what are the various binding pockets which are predicted by the software. So you can see the first site is predicted somewhere here. Then there is another binding pocket which is predicted somewhere here. So in this way, there are different binding pockets. So you can see the third pocket is predicted here. Then fourth pocket is predicted somewhere here. So in this way, there are 5 top binding pockets which are being predicted for this protein structure. So the property of human serum albumin is to bind to diverse range of ligand molecules. So this is what is mean for. So this molecule, this protein can have different binding pockets. So again, I gave a try and tried to run the same sitemap with the option called shallow binding pocket. So here is the option which is responsible for detection of shallow binding pocket. So I just gave a try and try to see which are the other pockets which are being predicted by sitemap in case of shallow binding pocket. So you can see even in case of shallow binding pocket, software has predicted a huge binding pocket for this protein structure, and you can see how big this binding pocket is. So similarly, it also has predicted some another binding pocket, and which is also huge and shallow in nature, which is responsible for binding of large ligand or different other proteins. So you can see third binding pocket, how much a big region it covers, as it is a shallow binding pocket region. So this is the fourth one, and then we will have last predicted binding pocket, which is shallow enough. So one of the striking thing means you will have deep binding pocket as well as shallow binding pocket results for the from the sitemap results. But we will try to see how it looks like in the particular score wise manner. And you can see these are the various sitemap results for shallow binding pocket, for deep binding pocket, and we will try to see how the score varies. So here you can see even for all those 5 pockets, you will have score like more than 1 point. So the first binding pocket is having score of 1.2, then 1.1, then 1.1, 1.016, and 0.82. So you can see, like in case of even deep binding pocket, the software has predicted 5 different binding pocket, and all pockets have d score value of more than 1 or zero point 0.8. So what does it means? All binding pockets are having capability to bind to at least different type of ligands. So one should not ignore any of the binding pocket in such case if you have multiple binding pockets with value more than 1. So definitely one should need to consider all this. So in a way it signifies that human serum albumin protein is able to bind to multiple type of ligands at multiple binding pockets. And same thing, if you see here in the volume section, there is a different wide range of volumes. They first of all, they have different d score, druggability score, and also volume is very much diverse in nature. So for example, for this particular site, volume is around 1885 cubic angstrom. It's a huge volume, so means big ligands can fit inside this pocket. But comparatively, if you see, there is another volume which is in 200 or 300 cubic angstrom, where comparatively normal size of ligand can fit inside it. So even smaller ligand can also fit inside this binding pocket, which is having volume having 154 cubic angstrom. So this is what the deep bindings pockets which are present in human serum albumin. And not only that, whenever I run calculations with shallow binding pocket to identify shallow binding pockets of the human serum albumin, as you have seen, it has shown bigger binding pockets which are present on the surface. So same, whenever I say bigger, you can imagine those bigger pockets from the values like 2112 cubic angstrom, then 977, 521. So in this way, it has predicted even bigger binding pockets as a shallow binding pocket. So you can see it from the volume, and not only that, even d score value for all those binding pocket are above 1 point. So it means all of those pockets are also druggable ones. So means those are able to bind to the various variety of drug molecules. So this is what the function of human serum albumin, and that perfectly makes sense for such a protein which has biological role in transporting your drug molecule or binding to your drug molecule in human serum. So in blood serum, like so this is the reason why such a protein is made up of various binding pockets, and the same thing is being predicted by sitemap also. So it increases the reliability and it also validates the sitemap results. So that's one of the aspect of sitemap result. And as you can see here, there is another example of human aldose reductase protein. So I am showing you this example because of specific reason. And what is that specific reason is this human serum albumin is the protein structure which is basically bound with the ligand inhibitor molecule plus a cofactor, and that cofactor is NADP. So this is the PDB ID 1US0 for this human aldose reductase protein structure, which is bound to NADP and the inhibitor. So again, as I said, once you download the protein structure from Protein Data Bank, you always need to prepare that protein structure through Protein Preparation Wizard. And once you get your minimized protein structure as a output, we can see how it looks like, how those ligand molecules are placed inside the protein structure using, let's say, apply custom preset. And you can see here there are two different ligand molecules which are present here. One is this particular ADP. I just try to change the color of it. So we can see it here. So in the simple way, I have splitted this particular molecule into two. These two ligands are being separated from the protein. So you can see there is one ligand which is NADP. It looks like this. And then there is another ligand which is an inhibitor and which is a little bit smaller than NADP cofactor. So this protein structure is specifically present with two ligands. One is cofactor and one is inhibitor. So there might be an obvious question like, do I need to consider this cofactor in the protein structure while performing molecular docking? So as I said, it is always depending on you, what type of research problem you are addressing. So as you can see, this particular protein structure has two ligands present in it, and the location of these two ligands is completely different in this sense. So let's see it in a detail. It has different locations in the protein structure. And so imagine if you are designing a competitive inhibitor for this NADP cofactor, then you need to remove this ligand molecule from the pocket before performing sitemap analysis. So means you want to consider this NADP binding pocket as a binding pocket for your molecular docking. So that's the reason whenever you want to perform competitive inhibitor for NADP or any cofactor like ATP or anything. So if competitive inhibitor you want to design, then definitely you need to dock your molecules at the same site where where cofactor is present. But if you are designing a non-competitive inhibitor, so non-competitive in case of non-competitive inhibitor, it might bind to some other place than the cofactor place. So in that case, you will have another binding pocket which is present in the protein where your non-competitive inhibitor can bind. So these are the two scenarios which you need to consider in your project and how to use it. So for example, in this particular protein example of human aldose reductase, you can see in surface view of protein, there are two different binding pockets. One pocket is responsible for binding to this blue color cofactor NADP, and another binding pocket which is present here is responsible for binding to inhibitor. So it means there are two different binding pockets you can use. So to consider to analyze it through sitemap, I have run sitemap on this particular protein structure of no inhibitor, no cofactor bound structure. This is the simple protein structure without any ligand or cofactor. And when I run sitemap calculations on it, and you can see the sitemap result shows the complete binding pocket as a single binding pocket because I have removed both ligands out of it. So if now the scenario is, if you want to design competitive inhibitor, then you need to remove that particular region of the that particular cofactor from the binding pocket and run sitemap analysis. If you want to design non-competitive inhibitor, in such case you don't need to remove cofactor from the protein structure because non-competitive inhibitor will bind somewhere else than the cofactor binding. So this is the inhibitor binding pocket and this one is the cofactor binding pocket. So in this way, one can consider whether which binding pocket you need to use it for the further molecular docking or grid generation exercise. And we'll just take a quick look of the sitemap result for this particular protein structure. And you can see the first site which is predicted for both cofactor and inhibitor. It has a site score of 0.98, which is almost around 1. So you can see this D score and you can consider it as a binding pocket because it has all druggability characteristics, but other sites which are having score zero point 0.7 or zero point 0.6, you can straight away ignore those other binding pockets. So this is the way you need to consider your sitemap results for further exercise, for further grid generation or further molecular docking. So coming to the next example, which I have shown you in the slides, is the protein structure for cytochrome BM3. And particularly, this is what the cytochrome BM3 structure is. And let's see how it looks. Yeah. So here is the example of your cytochrome BM3 and a protein FMN binding domain of the protein, and I just give it a different color, this protein structure. So you can see this is the protein complex, which is which you get it from the crystal structure 1BVY, and where green color is the cytochrome BM3 protein, and this gray color is the FMN domain of reductase protein. So this is what the crystal structure is present, and let's try to explore the various binding pocket of this particular complex. So what we'll do, as I said, you need to prepare your protein structure through protein preparation wizard, and once you get your structure from protein preparation wizard, you can run sitemap on this particular structure. So as I know, like I need to see the binding pocket which are present on this particular cytochrome BM3 protein. So I have extracted this particular chain, the single protein, and I run sitemap on this particular protein structure, and let's see how it looks like. So this is what the protein structure in surface view which you have. And once you have this protein structure in surface view with you, so there are different sites which are being predicted for sitemap, and you can see there is one site which is predicted inside the this red color region, means which is basically deep binding pocket where inhibitor or ligand gets bound. So this is what you can consider it as a heme binding pocket or ligand binding pocket for this protein called cytochrome BM3. Not only that, when I run second calculations using the sitemap shallow binding pocket predictions algorithm, I found the another bigger pocket which is present somewhere here on the surface in magenta color, and you can see this binding pocket is predicted at the top rank in case of shallow binding pocket. And let's see where this exactly pocket is present if you compare it with the original crystal structure. And you can see I have loaded the another chain of the protein structure which is FMN binding domain. I have loaded the deep binding pocket which is in red color. I have loaded the shallow binding pocket which is present in the magenta color. And you can see here specifically this shallow binding pocket of the protein is specifically present at the same place where your other protein gets bind. Your other protein gets bind. So you can see here this gray color surface of protein 1 and green color surface of protein 2, and protein binding region which is mentioned in the magenta color surface, which is predicted from again sitemap. So this is how sitemap exactly predicted the correct binding pocket for the protein-protein interaction, and you can use this information further for your grid generation or further your molecular docking exercise. And even if you look into the D score of this particular site, even shallow binding pocket is 1.033, and even for deep binding pocket the D score is 1.022, means it is more than 1, means it is definitely a binding pocket. So this is all about the binding sites which we have from the sitemap and how reliable it is. And then if you want to look into detail like how to modify structure or how to use these results for heat optimization studies, so we will see it in a detail for the example of particularly 2p33 protein structure. And we will try to see how it looks like or how to analyze these results. So I have just loaded the protein in surface view and the sitemap results here, which are having different patches, red and blue patches. And not only that, I also load the ligand molecule on the top of it just to see where the ligand gets bound. And then my aim is to modify the ligand molecule in such a way that it should form more interaction with the amino acid residues. So to get it simplified, I just hide the protein surface now and try to see my ligand molecule in detail way. So you have ligand molecule shown in green sticks and various patches which are mentioned here in red, blue color or yellow color. And there are these side points. So maybe I'll just hide those side points initially, just to make it clear. And now here is the example how to modify it. So let's imagine this is the red color patch which is responsible for hydrogen bond acceptor region in the molecule. You can see here this nitrogen with hydrogen is acting as a hydrogen bond donor, and so there must be a amino acid residue which is present here, and the red patch which is for hydrogen bond acceptor. So let's look into more detail. So I'll just, there are various type of surface, so I hide other surfaces and just try to see where are the chances where I can modify something. So here it is already satisfied at this particular region of the protein. It is already hydrogen bond donor is present. So let's see somewhere whether where I can modify something. So as you can see here, there is a chance. So this is the red patch which is present somehow near to this ring, and you can see this red patch can act as a hydrogen bond acceptor. So if I modify something here at this particular region, some functional group which is hydrogen bond donor in nature, for example hydroxyl group, or for example amino group with some substitution, if I substitute something here at this position, it might able to form the hydrogen bond with this red color patch. So this is the way you need to think of what to substitute and where to substitute. The same way, if I look into again detail and try to find out where can I modify something. So you can see here, this is the red patch which is present nearby this carbon atom, this hydrogen. So I can substitute something here again as a hydrogen bond donor group, like amino or hydroxyl group, and it might able to form the hydrogen bonding interaction with these red patch residues. So same way you can think of any other property like a hydrogen bond donor property, and we can see it where those properties are lying. So same way you will have some nearby properties like hydrogen bond donor property, and in this way here you can either, here also you can substitute some hydrogen bond donor to get interactions with this particular patch. So this is the way you need to analyze it in 3D carefully, and then you need to see where to modify and what to modify. This gives you the clear idea about some functional groups which are important for you to make your molecule more having more binding. So same thing can also be applied to hydrophobic. So yellow color region is for hydrophobic. So most of the hydrophobic patch is already being covered by like existing ligand molecule, but there are a few other small hydrophobic patches which are present far from the actual ligand. So you can basically build your ligand in such a way that with some middle functional group or long chain, and then it can form another hydrophobic group which is present somewhere in this yellow color patch. In this way, one can modify the ligand. We can think of modifying your ligand. So this is the way how one can use this information for heat optimization or further modification of ligand molecules. So this is how we use it. I hope it is a little bit clear for you how to use it. So for ligand modification, other than that, we can use the same information for grid generation. So grid generation means, now imagine you have this particular protein structure with you and there is no ligand present in it because ligand is not there now. But you run sitemap calculations and you got this sitemap result, and this particular site has this score more than 1. So you are now pretty sure about, I need to use this particular information from the sitemap for the grid generation for further molecular docking. So what I could do, I just need to go to task, browse, glide. There is an option called grid generation. You just need to click on grid generation, and there is an option called pick to identify ligand. You just need to change it to the entry. That's it. It's entry because the logical thing is this is sitemap is the new entry. So once you have this new entry with you, you just need to click on any of the point, this white color point which you have, any of the point. Once you click on point, it automatically covers the all points from this particular sitemap result, and it will give you the box. This box is nothing but your grid box. So that's it. You just need to single click on it. It will pick the complete site for your grid generation and click on run. That's done. It will create a grid box for you, and this grid you can use it for molecular docking. So that could be one of the way. In another way, if you have protein and ligand molecule present in it, so this is another case when you have co-crystallized ligand molecule present in it. In that case, everything becomes straightforward. So you will have protein structure, you know where the ligand is bound, you know the where is the binding pocket, because it's all clear from this co-crystallized ligand. So what I would do, I just need to go to task, browse, again same grid generation panel. Once you open this grid generation panel, you will have here by default molecule option on. You need to simply see this option like pick to identify the ligand wherever it is present. Then once you have this option on, you just need to click on any atom of the ligand. Any atom of the ligand. Just click carefully on any atom of the ligand, and it will show all ligand atoms are highlighted in green color boxes. So it means your site is picked, and you can see the again this magenta color box which represents your grid box. It will automatically identify this particular region as a binding pocket, and then you need to click on run. Once you click on run, it will generate grid for you, and you can use it for the further molecular docking exercise. So this is the way you can generate a grid for your molecular docking using sitemap result or using co-crystallized ligand present information present in it. Sometimes somebody can also ask the question like, in case if I have sitemap results with me, so how do I see like which are the amino acid residues are occupying this particular site? So the answer is simple. Like as you are seeing it in a surface view, same thing you can see it in a lines view, and we will try to see how it looks like. So I just hide the surface first of all, and on this particular protein I just show the lines, and you can see here there are this all of this protein is shown in the lines view, and you can see there are many amino acid residues which are surrounding to this binding pocket, but this is very messy to see each amino acid residue on the visualizer and to check what is the number of it. But as I said, Schrodinger is very user friendly, and you will have straightforward option to see what are the amino acid residues which are surrounding to this particular binding pocket. Just go to the project table. Option is in front of you on the top right. Just in project table, there are entries for sitemap. You know it is present in the property tree. So in sitemap, so far we have seen all properties which are primary properties like various scores, but to get the more information out of it, you will have some secondary properties. So in secondary properties, you will have the last option called residue ASL. So this residue ASL is nothing but the list of amino acid residues which are present in surrounding to this particular binding pocket. So for example, this particular binding pocket, I just hide primary properties, and you can have this list here. This is the complete list which you can simply double click on this particular cell, and you can copy this particular information for your if you want to note it down. So not only that, you also have information of the residues like chain A, what is residue number. Not only that, all residues are also listed here in comma separated manner from chain A. Let's say you just need to click on this cell, you can copy this information and you can paste it wherever you want to paste it. So same way, control C, control V, and this is the list of amino acid residues which are surrounding to this binding pocket. And you can use this information for any of the further studies. So this is the way it almost give you all type of information which is necessary for you to perform your computer aided drug designing project. So everything is in front of you, you just need to explore it. So this is what is all of the information. about the sitemap analysis and sitemap result. So here I would conclude the session with the acknowledgement to my team who are located in the Bangalore office, and we are always ready to help you out. So in case of any queries, please feel free to reach us, and you can always write us an email in case of any queries. So finally, thank you to the organizers, and thank you to all of you for joining us and listen the presentation carefully. I hope most of the doubts related to sitemap or binding site predictions are clear now. But still, if you have further questions, I would like to open the session for questions, and I am happy to answer your all of the questions. Thank you very much again. Over to you, Shelby.
Thank you, Dr. Paju, for that presentation. We have received a couple of questions. As a reminder to all of you, if you haven't submitted your questions, please do so in the chat window of the YouTube video. So the first question is, what is, in quotes, use more restrictive definition of hydrophobicity in sitemap panel?
So one of the easy answer for it is you always have help button for it. So you can see there is a sitemap, and so whenever it tries to see what is wherever this hydrophobic patches are present, you will have different algorithm like more restrictive and high restrictive means. Let's imagine whenever software tries to identify the hydrophobic patch, and if it finds two amino acid residues which are hydrophobic in nature like valine or isoleucine, then if it is small enough, then do we need to consider it as a hydrophobic patch, or we need more amino acid residues come together and form the hydrophobic patch? So this is what the less restrictive and more restrictive means. But as I said, like by default you have more restrictive option, means even there is a small hydrophobic patch made up of few amino acid residue, that information is also present with you, so it will consider it as a patch. So the same thing is applicable for this particular example. If you see, it is not only restricted to this particular big patch, but it is also showing some small patches which are present far from the binding pocket. So this is the way how software calculates it. And at any given point, if you want more information on it, so there is always a help button. So you can just click on this help button and it will give more information about this all options. So you will have this particular page where everything is written in a elaborative manner, and you can always read that information. Thank you very much.
Thank you for the answer. Moving on to the next question. So this is more of a general question. I get unknown residue X for the ACE and NME caps. Is that a standard notation in Schrodinger?
So X means something which is not natural amino acid residue. So X is just a ID. So because for your, if you are using cappings, so for example, your NMA capping or TBOC capping on the N terminal or C terminal, because those are not naturally occurring residues, so software consider it as a X. So it's a general nomenclature which everybody follows. It's not only about Schrodinger, but in any software you will have that notation for such such residue. I would not say it as a residue; it is just a molecule, some capping molecule.
Thank you. So the next question is how to determine that the ligand has desirable pharmacological properties.
So if you are, so I mean, pharmacological properties is nothing but like it depends on various pharmacophoric features like hydrogen bond acceptor, donor, or hydrophobic or ionization groups. So you will have tool called phase through which you can identify how many features are present in the pharma in your ligand molecule. So for that we have a separate session in consecutive days. So it will be discussed in more detail in those sessions, but you can simply visualize whether you have which type of functional groups you have, and it will also give you some idea.
Thank you. So the next question is, what if we get a D score below 1?
So, I mean, it's perfectly possible to get D score below 1, like zero point 0.9 or zero point 0.8. So, as I always says, if the score is more than 1 point, then definitely you need to consider it as a binding pocket. If it is zero point 0.9 or zero point 0.8, then you can consider it as a binding pocket. But if it is zero point 0.7 or zero point 0.6, then you can straight away ignore those sites.
So is the site size column in project table, is that for volume? And is the units of the same is cubic angstroms?
So size means it is something related to the area. Volume is completely different thing. Area is mentioned in angstrom square, and your volume is mentioned in angstrom cube.
Thanks. So the next question is, I actually don't understand this question, but I'm just gonna read it as it is. Um, so the question is, I understand why we set up everything from before, but is it possible to demo how to insert and prep all the items in the workspace navigator, especially the sitemap markers?
Yeah, I can show it to you. It's not a very difficult task. So, for example, let's see. So even sitemap markers or anything. Let's imagine you are dealing with the this particular structure with you. I hide the surface first, and this is the way your protein structure looks like, right? So my task is to separate the ligand and protein. What I will do, I need to split the protein and ligand. What I'll do, I'll just select this particular entry in the workspace navigator, right click on it, and there is an option to split. So just split it into ligand, water, and others. Once I split it, it will give me three different entry: one for ligand, one for water if it is present. So let's see, yeah, one for water and other for protein. So in this way, we will have three entries splitted. So based on your interest, if I want to go with simple protein structure, I will load it on the workspace and perform sitemap analysis on it. If I want to basically work with protein and ligand system, so I will same time I will load protein and ligand on the workspace. As I mentioned day before yesterday in the Maestro Visualizer training session. So whenever you have this blue circle on, means it is present on the workspace. Whenever you have this blue entry selected, it means it is selected. So if I want to load both, I'll go with load both and perform sitemap analysis. If I also want to consider water, I will load water on it and perform sitemap analysis. So this is the way which one can go further with which you can load it. This is about protein and ligand. The additional thing is now if somehow I want to merge these two entries. So I have protein in this green color, I have ligand in ball stick view in magenta color, and there are two separate entries present here, but I want to somehow merge it. So what I would do, I would simply select those two entries in blue color, right click on it, and there is an option to merge it. So I'll just merge it and it will create a new entry for me, which has, you can see there is a single entry which has protein and ligand present in it. So this is the way you split and merge. And now coming back to your sitemap result analysis, and here is the sitemap results which you will have. And you always need to remember whatever you have present on the workspace, the same thing is also shown in the structure hierarchy section, which is here. So in structure hierarchy section, if you expand, you will see what is present here. So this is the sitemap results which you have. Apart from patches, you have these site points. You can see it is selected. as the same way it is selected in structure hierarchy. I can hide those points. I can show those points. You can see here, I'm just using this tick button to show and hide these side points. If you want to play with this side points rendering, there is a plus button and you can always play with it. You can show it in balls view, you can show it in some small balls or some sticks or whatever you want. The size you can manage. So this plus button is always in front of you to play with whatever is loaded on the workspace. So just to show you, I have changed it to ball stick view, and that's why it is showing little bit bigger points. So this is the way you can show and hide it, and because these are various patches are nothing but the surface. So whenever you say surface, you will have this S button in front of every sitemap result, and you can see there are various surfaces present here: hydrogen bond acceptor, hydrogen bond donor, hydrophilic, hydrophobic, or surface. So you can always on it or off it based on your requirement. So this is the way we can play with the surface, right? And let's see, for even for surface manager we have something good thing, like this is the quick molecular surface we have in mesh view. So if I want to play little bit with this surface view, so here is the manage button which you have. If I simply open this manage and see which surface I am playing with, so this is the first molecular surface I want to play with. So I can change its display options you have here, and I want to change it from mesh to solid, and just say OK, and it will show me this particular surface in solid surface view, right? And the same thing, if I want to change it to, let's say, dots, I can change it. It will show me the same surface in dots view. If I want to increase some transparency of these surfaces, you can see this solid, and there is an option for transparency. I can change this transparency to, let's say, 50%, and say okay. It will show me the transparent surface. If you can point it out now, surface become transparent. So these all options are present. It's all customizable. There is a toggle button for surface show and hide. You can quickly hide your surface or show your surface using this toggle button. So options are present there. The only thing is you need to explore a little bit. Most of the things I have already mentioned in my previous presentation on Maestro interface. So if you go through that presentation carefully, you will find almost all options which are of your interest. So we need to go through it carefully. Everything is present here. Thank you.
Thank you for that explanation. I hope that is what you were asking. If there is anything in particular you want to do and you're not able to do it, we can obviously you can ask us during the Q&A sessions as well. So the next question is, can we use this to check how a drug molecule or small peptide changes the relative configuration of the protein subunits, or is that a job for Desmond?
Yes, you are right. It is a job for Desmond. Whenever you are thinking about conformational change, you need to go for molecular dynamic simulations. And there you will find the answer after running MD simulation.
So the next question, I think you already went over it once. So the person asks, sir, for some protein of COVID-19, I got only one single binding site using sitemap, and that too, it had less than 1D score.
Yeah, I mean, if you don't have choice, but still D score makes sense. If it is less than one, like I could imagine if your less means zero point 0.6 or zero point 0.5 or something. So if it is so, then as such there is no drugability present in that particular site. But still, if you want to proceed with that site, then you are free to go ahead with it, and who knows what makes sense afterwards. So you can go ahead with it in case. But if you want to rely on that t score value, then the answer is it doesn't have that much druggable properties.
Thank you. So the next question is more of a general question. So why do we need to do energy minimization?
So we do energy minimization to relax your protein structure, to optimize bond lengths, and to reduce the steric clashes. So this is what the general idea of doing energy minimization, to get the relaxed conformation.
Thank you. The next question is what are the algorithm used in this software for docking, for example, for RRD, QPLD, and IFD, etc.?
So regarding docking, we will have separate sessions, I guess tomorrow. So we will discuss it in more detail.
So the next is also a general question. What is the essential purpose of force field parameters in docking and other computational processes?
So, I mean, in general, force field defines how molecule behaves. So, behaves means, for example, just a simple example is whenever carbon is binding to another carbon through covalent bond, through specifically single covalent bond. So, how much is the bond length? It is 1.44 angstrom. So, this is what is necessary to keep that two carbon bounded by single bond. So this is what the force field governs. So force field in force field parameters, it is already mentioned that whenever carbon is bound to another carbon through single bond, please maintain the distance at 1.44 angstrom. So it is all mentioned in the force field. So in case of if there is a distance between two carbon is less than 1.4, like 1.2 or 1.3, then it can be a double bond. So this information is also mentioned in this force field. If it is less than that, then it is the triple bond, carbon carbon triple bond. So means this bonded information, you will have similar way angle information, you will have similar way torsional torsion angle information. So these all things are present in force field, and somehow force field tell your software how should you keep your atoms in a molecule, bounded to each other, non-bonded to each other. This all information is present in force field. So it governs how molecule behaves.
Thank you. Moving on to the next question. How to differentiate between the cofactor binding site and inhibitor binding pockets in a protein?
So the simple answer is by visual inspection. You need to see it visually, the protein where inhibitor is bound, as I showed in the demo, where cofactor is bound, and you need to critically analyze it.
Thank you. Moving on to the next question. While designing competitive inhibitor after removing the cofactor, whether we have to retain the co-crystallized ligand?
So whenever we are designing the competitive inhibitor, it means there will not be any other inhibitor bound in the protein structure, because that's the external moiety. So the example which I have shown you is having already inhibitor and cofactor bound structure. But in case of competitive inhibitor bound structure, you will not have cofactor bound in it. You might have inhibitor bound to the same location where cofactor used to bind, and there will not be any other inhibitor present somewhere else. So that all, after analyzing the structure of your interest, you will come to know about it.
Thank you. So the next question, I think the question came before. You actually explained this later, but if you want to just go over that again, please kindly elaborate on the significance of small white balls, red volume, and the blue volume in the binding pockets.
So this is what I have explained, like these points are your site points, and red and blue patches represents hydrogen bond acceptor and donor feasibility properties which are present in the binding pocket and amino acid residues. So I would suggest you, after this presentation, after this session, you can revisit the YouTube link and try to see it again in detailed manner.
Thank you. So the next question is, if the structure is a model structure, not a crystal structure, and the template similarity between the template was about 50%, then how do you predict the binding pocket side and how to authenticate it?
So how to predict? Answer is sitemap. How to authenticate it? You can check the D score if it is good enough, and then how to validate it. So validation comes only after experimentation. If you do experiments on the same protein or same ligand, if you get the same good biological activity against that particular binding site, it means it will validate your results in case of the new protein structure.
Thank you. So the next question is, can you please show how we can differentiate between the shallow binding pockets and the deep pockets?
So normally deep pockets are smaller in size. Let's say the volume is around 500 angstrom, cubic angstrom, or 300 cubic angstrom. But shallow binding pockets are really big in size, and those are mostly present on the surface of protein. And those their volumes might be like 800 or 1000 or more than that cubic angstrom. So you can differentiate between it by visually inspecting or looking at the volume of this particular volume.
Right. So the next question is, does sitemap have an option to show the different shapes of the same binding pocket?
So as you have seen, like it also gives you the shape of binding pocket. So you can just create a surface of your sitemap result, and it will show you the shape. So maybe I can just quickly show it to you one more time. So let's imagine this is the binding site which is predicted here. And if you create a surface of this particular binding site using this plus button, if you create a surface of it, it will show you the surface view. And in this surface view, you can see the shape of it. What is shape of it? You can differentiate like X shape, Y shape, square shape, whatever. So this is the way. It's a matter of analysis. It's a matter of visualization.
Thank you. So the next question is, sometimes our test ligand might go and bind to some other binding site rather than the binding site of the co-crystallized ligand. Um, okay, yeah, that's the question.
Yeah, it is feasible. I mean, as we say, we have seen like a protein can have multiple binding pocket. You can call it as an orthosteric pocket. You can call it as an allosteric pocket, and it's perfectly fine. It depends on the biological event.
The next question is, where can we find the D scores of different pockets?
So it is already present in the project table. You can check it in the project table itself.
Thank you. So the next question, in what step do we remove the ligand, the co-crystallized ligand, and what is the necessity to remove the co-crystallized ligand?
So at what step you need to remove? Once you prepare your protein structure through protein preparation wizard, after it is prepared completely, means after energy minimization, you will have prepared protein. After that, you can remove the co-crystallized ligand from your protein structure in case if you want to run sitemap results. And then what is the significance of it? Means to run sitemap or to analyze these particular sites through the software, you need to have that empty pocket. That's why we remove ligand from it, to make pocket empty.
Thank you. So the next question is, when we import protein from protein data bank, it already has a co-crystallized ligand. So already binding site is known here. Then why do we opt for sitemap tool?
So as I said in the last part of demo. In case if you have ligand bound structure from protein data bank, then you don't need to go for sitemap. You can simply use that information for receptor grid generation. And as I showed, you can simply open the receptor grid generation panel and click on any atom of the ligand, co-crystallized ligand, and it will automatically identify the site. There is no need to go for sitemap until unless you want to analyze the binding site properties separately. Yeah.
Thank you. So the next question is, can we change the color of each sites into different colors?
Yeah, it's perfectly fine. Like you can change the colors. So just create a surface, or there is an option to change the color, which I have already mentioned. So you can go through it again and see how to change the color. So changing color is not an issue. It's just simple change color option.
Thank you. So in the binding site, can we see the hydrogen bond bound residues?
Yes. So if you hide your surface, you will see your protein in lines view, and in lines view you can see your amino acid residues also. Maybe I can just quickly show it to you. So you have let's say protein structure with you, which is here. You have ligand molecule present in it. You have the sitemap results present here. You can just go to preset and apply custom preset, and it will show you all those amino acid residues which are present here and which are bound to the particular site. So for example, I just hide this quick surface and let's say hydrogen bond acceptor. For simplicity, I also hide let's say these site points, and yeah, you can see here the various patches. For example, though it looks messy, but let's see it critically one by one. For example, I am highlighting right now is the this particular patch which I would like to highlight. This is the oxygen from your ligand molecule. This is the amino acid residue nitrogen, and there is a hydrogen bond between it. And this red patch represents hydrogen bond acceptor property of the ligand. And then if you label this particular residue, you will find what residue it is. It is aspargine some 152. Yeah, aspargine 152 residue is forming hydrogen bond interaction. So it's pretty simple. You can just go to preset and apply custom preset. I hope it answers the question.
Yes, thank you. Moving to the next question. Is there any option to view this in the 2D viewer?
So you cannot view sitemap results in 2D viewer. Faces are something which is 3D, not 2D.
The next question.
The molecule which consists of let's say quinoline. So you just draw a structure of quinoline and provide it as a substructure, and there is option to perform substructure search. So whichever molecules are having quinoline in their structure, it will filter those molecules for you. So this is called substructure search. Means just searching that particular structure, substructure in the complete structure of molecule. So you can always visit the database presentation on the same channel. You will find the answer.
Thank you. There are some more um, questions that are sort of related. So, what binding sites are more reliable from site maps? Also, if we have binding pockets with same D score and all are more than one, which one should we choose?
So ideally, in such case, you need to go for all binding pockets individually, one by one. You need to generate grid separately for each binding pocket in such case, and you need to perform molecular docking in each pocket separately.
Right. And the more reliable ones are where the D score
Yeah.
is more than one. or about one, around one. Okay. Could we predict the binding score for a ligand if other ligand is bound in the protein structure without removing the bound ligand?
So I think that question
I,
needs to be
yeah,
there.
I think it could mean if they could find other binding sites, if I'm not wrong, other than the ligand, the binding site where the ligand is already bound.
Yeah, in such case, yes, it is feasible with molecular docking. You need to keep your first ligand in the binding pocket. Same, you need to generate a grid around another binding pocket and dock your second ligand in that another binding pocket, and you will get the score of.
Also, it could also mean like how well the ligand is bound. Is there a measure to do it? Um, is there a way to find the binding score? I think they're asking for the MMGBSA
Yeah,
sort of a thing.
if you
Yeah.
are asking for docking, then yes, the docking score is also feasible using molecular docking exercise. If you are asking for binding free energy, that is also feasible with MMGPSA module. So both things are possible. It depends on what you want.
Yeah, and I think we'll be going over this in other sessions also about specifically about docking and how to validate that, how to know what is good score and other things. So the next question is, once we have set our working directory, will all work, including sitemap analysis, be saved there automatically, or do we have to save it every time?
So as I already explained, once you have specified working directory, everything will be saved there itself automatically. You don't need to save anything separately. Everything will be automatically present there. Just go to that particular folder. You will find all of your data.
Is it valid if the binding pocket is very big and our ligand is very small?
Yeah, it's perfectly fine. It is possible.
If our protein is having more than one chain, should we remove the other chains? If so, please tell the criteria for selecting a specific chain.
So you need to ask the question to yourself where your binding site lies. So if your binding site is present in, let's say, chain A, then you don't need chain B. But if your binding site is present at the interface of chain A and chain B, then definitely you need to keep chain A and chain B for your further studies. So that's the answer.
Thank you. The next question is the uh, oh yes, how do you change the background color to white?
So for that, I would suggest you to please visit the day before yesterday's presentation on Maestro. So these things are explained in this Maestro tutorial in ISO. Please do visit that video.
Yes, and this particular point was already covered. So just go through the video again. Um, the next question is, how can we design competitive inhibitors by screening of unknown ligands by hit and try method?
Yeah, it can be the molecular docking can be the method to answer this question. So we will have session tomorrow on
Yes, I think your voice has is low now.
it. Okay.
Um, yeah, okay. So the next question is the first binding site, is that the one with the highest D score?
So not necessarily, but it is sorted based on site score. So most of the time, whichever site is having highest D score gets up on the top. That might be the site two as predicted. Maybe that can be a site three as predicted one. But you always need you don't need to look for site one, two, or three. You always need to look for D score or site score. That's the best criteria.
Okay, the next question is, in theory, you mentioned that same binding pockets can have different shapes. Is that something we can identify?
Yes, you can study that one in different protein, different structures of the same protein.
Thank you. How to differentiate? I think you already talked about this. Um, I'll just quickly check the YouTube chat if there were new questions. Yes, so the one last question for you is how to find DNA binding site in protein structure. I have a complex, but I don't know binding site, so I need to separate them and use sitemap for the same.
Yes, you can use prediction of shallow binding pockets. Because DNA is a big structure, it needs more space to bind. So just on that, detect shallow binding pocket option, and it will show you some probable binding pockets even for DNA or RNA.
Thank you. I think that's all. Those are the all questions, and we received a lot of appreciation for this particular session. I think there were a lot of queries about sitemap in yesterday's session as well, and thank you for addressing all of them, Dr. Prachul. I just have a small announcement for you guys. Um, I'll just quickly share my screen. Um, I if you can, yeah, thank you. Okay, I hope you can see my screen now. Um, the one announcement that I wanted to make, and some of you asked me yesterday if there are other SOC, which are Schrodinger online course sessions after November 2nd. The answer is no. There are no more sessions in 2020. There might be some in 2021 next year, but we don't have the schedule for them now. So please, if you are interested in SOC and you want to avail the discount that the codes that we have sent you, please register. The end date is October 26th. So make sure that you register and pay before October 26th in order to avail the discount. As I told you again, the discount codes are sent to you via email. If you haven't received these emails, please write to us at ddcourse@schrodinger.com and we will send you these codes again. um, for the SOC, you will require a Schrodinger website account, and as well as for the evaluation license, for that as well you will require the website account. So please, if you do not have one, please go ahead and register and get a website account at www.schrodinger.com/request-account. um, so once you have the account, you can register for the SOC, as well as you can download the Schrodinger software. The other announcement is that we have Q&A sessions, which are called office hours, every Thursday from 4:30 p.m. to 5:30 p.m. So if we miss any of your questions and if you have any additional queries, you can join us. All of us will be there. We will take up any of your questions. This is held on Zoom. The link, how to join, and the password for the Zoom meeting is there on the course website page. So if you go to schrodinger.com/dd course, that is the short URL for the course website page. So you can go there and you can see the Zoom link and the password for the same. Again, evaluation licenses. We are reviewing all the requests that we have received on the evaluation request form. We really appreciate your patience in this regards. We are going through it. We have received a lot of requests, and we are looking at them and sending emails to you and sending licenses to you. I think some of you have already received the licenses. Um, Again, we haven't reviewed all the requests. We have received a lot of them, so we are doing that and sending you the emails. So only after we send you an email, please send us the information of machine ID, because there is a particular way in order how you have to send it to us. So please do not send it before you receive an email from my colleague Kishore. So once we review your request, we will send you an email. Kishore will send you an email and explain the instructions, how to download, install the software, and what is the information that we require. So please make sure that you wait for that email. Only after you receive that email, you send us the machine ID information. There's the entire file that you have to send. Please do not just send us the MAC ID and host name. We don't only require these, we require the entire file. And we are sending you the instructions. Please go through those instructions and send us the required information once you receive that email. um I think the other question that I've been receiving is, how do you get the certificate, and do you get the certificate? Yes, at the end of this course, we have an evaluation, which means we have an assessment or an assignment for you. If you qualify that assignment, we will be sending you the certificates. These will be an in the form of e-certificates, so you'll be receiving those. You do not have to participate in evaluation or in SOC in order to get these certificates. um, but you have to be registered in this course. So if you go to the course website, which is schrodinger.com/dd course, you can register for this course, this particular course, and you will be receiving the assessment at the end of this course, that you can fill out and send it to us. And if you qualify, we'll be sending you the certificates. SOC certificate is totally different. SOC is a curated course, self-paced course that is hosted on our website Schrodinger, and you also receive a cloud instance where the Schrodinger software is installed. So you don't have to install software on your computer in that case, only if you're going for the SOC, which is Schrodinger online course. Once you complete that course, you will receive a, a certificate, a badge that you can link to your LinkedIn profile, and also you will become a part of the alumni page on the LinkedIn. So that's all the announcements that I have for you today. Please join us tomorrow for another demo session. If you have any questions, please write to us at ddcourse@schrodinger.com. That's it for my end. Thank you for joining today. We will see you all tomorrow. Have a great day. Bye bye.